All right. Today we'll study a particular kind of wave, a mechanical wave. A mechanical wave meaning a wave that needs a medium to travel in. So, for instance, electromagnetic waves don't need media. So it's a mechanical wave, and we're going to talk about a particular frequency range. Okay, so you are born with a couple of sensors that can detect this frequency range. They can detect sounds of frequency range 20 to 20,000 hertz. Okay, you have to be younger to be able to hear a higher range like that. Okay, so my hearing probably stops working around maybe 9,000, 10,000 hertz. Okay, all right. There are mechanical waves of lower frequency and higher frequency. There are biological systems that can hear higher frequency. Dogs, for instance, bats, and so on. Okay, and elephants and larger animals can hear lower frequencies. Turns out that lower frequencies travel a longer distance, so you want to be able to adapt to listening to lower frequency sounds. Okay? So if you're an elephant, you have to have a large range of grazing range. And if you gotta tell your buddy 5 kilometers away that, hey, listen, there's a nice sugarcane field here, you gotta, you know. So anyway, so we're going to talk about sound waves today. They're mechanical waves and they need a medium to travel in. Okay? Now there's a lot of slides in here, so I'm just going to give you the punchline on slides. Okay? You guys can read all of that. So here's how you produce sound waves. Okay, you take a diaphragm and oscillate the diaphragm or make it vibrate. Okay, and when you make it vibrate, what it does is it pumps energy into the surrounding medium. Okay. Now, right now we'll start off by looking at pumping energy into the surrounding air. That is, you produce sound waves that travel through air. That's what we're looking at. Okay. You can pump energy on this table, okay, and waves will travel away from, energy will travel away in this medium. Okay. Now here's an interesting fact. Okay, so okay, as a speaker oscillates back and forth, it transfers energy into air, mostly as thermal energy. Okay, so mostly you generate heat. A small part, about 1% of the speaker's energy goes into compressing and expanding the surrounding air. So if this guy is spending 100 joules a second, that's 100 watts. Okay, 1 watt is going into the sound. Okay, and 99 watts is generated. I mean, heat is generated. All right. In a fluid, what is a fluid? Liquids and gases are fluids. In a fluid, you only have longitudinal waves traveling. What are longitudinal waves? If that's the direction of wave travel, each particle is oscillating parallel to the direction of travel. Okay? In a solid, you can have both longitudinal and transverse wave travel. Okay, so in a solid, you can generate both longitudinal and transverse waves. Okay. You cannot do this in a liquid because, see, when you do a transverse wave, what you do is, let's say if this atom oscillates in that direction, you have to have forces to pull it back. And a liquid, those are called shearing forces, and a liquid can't support shearing forces. Okay. All right, so through the ground, through this table, you can have both longitudinal and transverse wave travel. All right, so to generate a sound wave, you have to have a source that is pumping energy into the medium. So here's a piston that oscillates. Okay, that's the source that's producing the sound, and it's pumping energy into the fluid. Okay. Now, in a fluid, the sound wave is a longitudinal wave. So this could be air, this could be water. Okay, let's look at this. So what's happening? So when this thing moves to the right, it compresses the air closest to it, and then when it moves to the left, there's a slight lower pressure that's generated. Okay, so what you have is, see, higher density, lower density, higher density, and this pattern travels. So you can think of the sound wave as a pressure wave. See, here's a higher pressure, there's lower pressure, higher pressure, and so on. So this pressure wave travels. All right. Also, if you look at, so let me show you an illustration. Okay, so here's a longitudinal wave. So in a longitudinal wave, okay, so here's the high pressure, low pressure, and that wave is traveling, and each air molecule is oscillating parallel to the direction of travel. Okay, so keep that in mind. Okay, and now what this graph is showing you is, so you have the high pressure location. That molecule is in equilibrium. At this region, okay, the molecule is going in to the left, so its displacement is negative. And at this location, the molecule is going to the right. And that's how the high pressure region was created. Okay, so these molecules are at rest. These guys are oscillating, are over here. These guys are over here. Okay, that's what this is showing. So what this is showing is the displacement curve is 90 degrees phase shifted from the pressure curve. Okay? You can study this diagram later, but don't worry about it. So what I want you to remember is how are we generating? A source is oscillating, that's generating a sound wave in this medium, and you can think of this sound wave as a pressure wave or a displacement wave. Okay? And so here's the pressure wave, there's the amplitude of the pressure. Okay? And here's sine kx minus omega t. Which way is this wave traveling? You guys learned that?
To the right.
To the right. What is k? K is the wave number, which is related to the wavelength, 2 pi by lambda, and omega is related to the frequency, 2 pi m. All right. And the pressure amplitude is related to the displacement amplitude. Okay. So sound waves in fluids are longitudinal waves. They travel through any material medium. Their speed depends on the property of the medium. Okay, so remember that. The speed of sound depends on the property of the medium. So for instance, and you will learn in a little bit, for longitudinal waves, the speed is related to the bulk modulus divided by the inertial property, so say density. So for instance, in air, sound waves travel at 350 meters per second, 340 meters per second. In water, they travel about 5 times faster. Okay? And so on. So wave fronts, okay, so here's a so what is this? This is, let's say, an oscillator hitting a ripple tank, and it's generating waves. Waves are crests that were generated, wave fronts are crests that were generated at the same time. Okay, so these are wave fronts. Okay, and the reason we talk about wave fronts is energy travels perpendicular to the wave front. Okay. All right, so you guys understand what wave fronts are? So there are crests or troughs created at this, generated at the same time. Okay, so planar, circular, and spherical wave fronts are possible. Planar, you have a plane wave front. I guess so from the sun, what is reaching us is a plane wave front. And spherical wave fronts are if you have a point source of light, you know, it generates spherical wave fronts and so on. So wave fronts are surfaces of constant phase. Okay, so we define sound waves as human-centric. The definition is human-centric, okay? What we can hear is how we define things. So we can hear from 20 hertz to 20,000 hertz. That's the frequency range we can hear. Okay. Of course, sound waves can have any frequency. Okay. Well, in principle, you can't have infinite frequency, but but our sensors work in that range. Okay. So teenagers can hear frequencies of 10,000 hertz and above, but retirees cannot hear them. What is this? Is this, is this fact useful? Why are we talking about this? People actually use this. If you go to a mall and you go to an expensive store, and if they want to keep the riffraff out, the teenagers out, they just play a high-pitched sound. It bothers the young teenagers, so they don't come in. And the older people with money, they can't hear it. The flip side of it is, I'm sure some of you guys have used a high-pitched tone in schools as your ringtone, and the teacher can't hear them. Has anybody used a ringtone like that? Okay, so anyway, now you can do that. So if you use a ringtone that's higher pitched than 10,000 hertz, I won't be able to hear it. Yeah. All right, so anyway, so this shows you, okay, we will learn this graph in detail. So this is the range we can hear, okay, and see there are all kinds of applications. So underwater communication, sonars use frequencies higher than that. Bats use these higher frequencies for echolocation from 60 to 100,000 hertz and so on. And you see threshold of hearing. Okay, so we'll talk about the decibel scale in a little bit. Threshold of hearing. As you get to lower frequencies, the sound intensity or the decibel level has to be quite loud for you to start hearing it. Okay, so your hearing depends on the frequency as well. Your ears are most sensitive to about 3,500 hertz. Yeah. So infrasonic waves have frequencies below the audible range. So infrasonic frequencies are below 20 hertz, and ultrasonic waves are about 20,000 hertz. dog whistles are ultrasonic frequency whistles. Okay. Dogs can hear frequencies higher than we can hear. So the speed of sound in a medium depends on its elastic property divided by inertial property. Okay. And this is true for all mechanical waves. Okay. So here's speed of sound in various media. Okay. So for longitudinal waves, sound waves traveling in solids, liquid, or gases, this is for longitudinal waves, the speed of sound is the bulk modulus divided by the density. So here's the speed of sound in various media. Okay, so for instance, in air, it's about 340 meters per second. Sound will travel from here to Mainland High School in 1 second. And in liquid, in water, it's 1500 meters per second. Yeah. So sound would travel from here to Bethune-Cookman College in 1 second. Okay. In iron, it's 6,000 meters per second. Yeah. Okay, we spend most of our time in air, and that's the sound waves come to us traveling through air. So here's the speed of sound in air is given by that formula. Gamma is the ratio of specific heat, so you'll learn about that in physics too. This is the temperature in the Kelvin scale, and that's the molar mass of air molecules, so average molar mass. Okay, so here's the speed of sound as a function of temperature in the Celsius scale. So at 0 degrees Celsius, it's 331 meters per second. And for each degree rise in temperature, the speed of sound increases by 0.6 meters per second. Okay, this stuff is important. For instance, okay, so let's say if you're a concert concert flautist, you play the flute. Okay, so here's the speed of sound, which is frequency times wavelength. The wavelength depends is on the length of the flute. Okay, the length of the flute doesn't change. So as the speed of sound changes, the frequency it produces changes. Okay, so you gotta, so they have to tune their instrument, and depending on if they go to a cold hall or a warm hall and stuff like that. Okay. So this is just little fun facts. Here's the speed of light. Okay. The speed of light is 300,000 kilometers a second. The speed of sound is 0.34 kilometers a second. Okay, so light travels 1,000,000 times faster than sound. So if there's lightning, you always see the lightning flash first and then hear the thunder. Okay? And here's a rule, the 5-second rule. So if you hear the thunder 5 seconds after you saw the lightning, that was 1 mile away. Okay, so if you hear the thunder 10 seconds after you saw the lightning flash, that's 2 miles away. Okay? And if you heard and saw it at the same time, then that's probably the last thing you did. All right. All waves carry energy. Okay. So sound waves carry energy as well. So for instance, when somebody's talking, the sound waves get to your eardrum and energy is deposited onto your eardrums. And that eventually gets converted to a nerve signal, which is sent to your brain. Okay, so what is happening? This piston is pumping energy into the medium, and the sound wave carries the energy away. Okay. Energy is propagated away from the piston by the sound wave. Soon as you stop pumping energy, the sound wave dies. Okay? And there's no more energy being carried away. All right, so what you're interested in the following, so here's the piston that's pumping energy, and the sound wave is carrying away the energy. And let's say you're standing there and you want to ask how much energy is passing you per second. Okay. And the more energy is that's passing you per second, the louder the sound. Yeah? So the power is 1/2. Rho is the density of the medium. A is the area of cross section that you're looking at. V is the speed of sound. Omega is the frequency, and S is the amplitude of the particles oscillating. Okay. So the power always depends on frequency and amplitude squared. Okay, so this is a common feature. Intensity is defined as power per unit area. So how much energy is passing you per second per unit area? That's intensity. Okay, so again, intensity of sound is proportional to square of the displacement and square of the frequency. Okay, so what this is showing you is this is a point speaker, and if it's emitting sound uniformly in all directions, the intensity at distance r, so this the intensity is, okay, so if you have a point speaker and it's emitting sound in all directions, so the intensity is power divided by the surface area, and that's the surface area of a sphere, which is 4 pi r squared. So this could be a little bird singing, and the intensity of sound at distance r is that. Intensity of sound at twice as far away is 4 times less. Okay. Okay, so here is an interesting fact that most people are not aware of. Anyway, so let's say so this is you, and 3 pianos are playing. Okay. And let's say now you want to hear it twice as loud. Okay. How many more pianists need to play? Or what was that? Violinist or pianist? What did you say?
Pianist.
Okay, pianist. Okay. So do you guys understand what I'm saying?
Yes, sir.
So you have 3 pianists playing, you're listening, and now suddenly you decide you want to hear it twice as loud. We're going to keep their level, intensity level the same. How many more pianists need to play?
27.
27? What would be your guess? I mean, you're a college student.
4, 5, 5.
Hmm?
I was asking if 5 more or 5 total.
It turns out that 10 times more. 30 pianists need to play at the same level for you to hear it twice as loud. Okay. It turns out that, so if this is the intensity, your sense of loudness increases logarithmically, like how that increases. Okay. And this is, we have adapted that because you want to be able to hear a large range of intensities. Okay. You don't want to devote too much of your processing power. This is your brain. Okay, so apparently, so you can hear intensity of watts per meter square and 1 watt per meter square. This intensity hurts, and this you can hear, barely hear. This is your threshold of hearing. So the intensity level you can hear is, you're sensitive to, is a trillion-fold high. But your sense of loudness is not a trillion-fold high. Okay, so if a tiger is coming after you, sneaking up on you, and you want to hear that rustle of the leaves, and you don't want to be scared of a thunder. You know? All right, and this is true for all your senses, for your sense of taste and stuff like that. So heat, something hot and spicy, you're always logarithmically sensitive. Did you guys understand that? All right, so now you also know why those orchestras have so many violinists and all that. You know? So your range of loudness can be controlled, or your experience of range of loudness. Okay, so we define, since your sense of loudness depends on the exponent, we define as decibel scale. So the decibel scale is logarithm of the intensity. Okay, so here's how the decibel scale is defined. Beta is 10 log of intensity divided by I naught. I naught is the threshold of hearing. Okay, that's the softest sound you can hear. Okay, so I'll go over this again. All right, so we said a lot. Again, you hear 3 violins in a simple picture. If you want to hear it twice as loud, how many violins do you need? 30. If you want to hear it 4 times as loud as the original, I'm sorry? 300.
10 to 40.
Yeah. All right. So the humans can detect, now that's a simplified picture, but anyway, that's roughly correct. Okay, humans can hear intensities in the range of 10 to the minus 12 to 1 watt per meter square, a trillion-fold range. Okay, obviously the threshold of pain does not correspond to a trillion times louder sound. Okay. The perception of loudness is more accurately described by the logarithm of the intensity. Okay, so the perception of loudness depends more on the exponent, okay, of the intensity. Hence, it is useful to define decibels. Okay. So, if you put I naught here, that's 1. Log of 1 is 0. So the threshold of hearing is 0 decibels. Okay. And the threshold of pain is this, would correspond to 1 watt per meter square. This is 10 minus 12. That becomes 10 to the 12. Logarithm of that is 12. 12 times 10 is 120. Okay. Threshold of pain is 120 decibels. That sound would hurt. Okay. So that's why when you go to the airport, all those guys directing the jet engines, they always have to wear earmuffs, okay, because those sounds are 120 decibels and more. Okay. You go to a race, this is a racing town, all those guys in the pit crew have to wear those earmuffs. Okay. Okay. An increase in sound level by 10 decibel corresponds to increase in, will sound twice as loud. So we'll get to that. So 15 decibel sound, 25 decibel sound is twice as loud. Okay. So loudness is a psychological response to sound and depends on both intensity and frequency. As a rule of thumb, doubling in loudness is approximately associated with an increase in sound level by 10 decibels. So here are some sound levels in decibels. Nearby jet plane, 150 decibels, jackhammer, 130 decibels, and so on. Okay. Mosquitoes buzzing, that's 40 decibels. I don't know if your prolonged exposure to high sound levels can seriously damage ears. Also, noise pollution can contribute to high blood pressure, anxiety, and nervousness. So, so this instrument that you're born with, the detectors of sound, they're pretty amazing instruments. The perception of frequency is called pitch. Typically, humans have excellent relative pitch and can discriminate between two sounds if their frequencies differ by 0.3%. So you can tell the difference between 500 hertz and 1.5 hertz. The perception of intensity is called loudness, and you can discern differences of about 1 decibel, and a change of 3 decibel is easily noted. Okay, so intensity is watts per meter square. Decibels is log of intensity. Okay, so this is a scale used for loudness. Okay, so this is something an instrument can measure, and decibel is also something an instrument can measure. But your ears depend on, their sensitivity depends on frequency as well. So this is the unit for hearing of loudness. Okay. So you see, there's the sound level in decibels. So for the instrument, you can build an instrument that is insensitive to frequencies. I mean, that its sense of loudness doesn't depend on frequency. But this is your ear sensitivity. So this is 0 fawn, this is 10 fawns, and you see, so near here, near 100 fawns, 100 fawns and 100 decibels are the same for up to 1,000 hertz. So 100 fawns and 100 decibels are the same, okay? All right, so the horizontal curves are instruments, and these curves are your ears, okay? And this is what the doctor's office is testing when you go to the doctor's office. Okay. Do you guys understand the difference? All right, so this is what you can hear. Okay, these are ultrasonic frequencies, these are infrasonic frequencies, so these are sonic frequencies. Sonic frequencies meaning your ears can detect them. Okay, you don't want to hear sounds louder than that. That's 120 decibel, that's hertz. Yeah. And below 0 decibel you can't hear. Okay, so you can't hear sounds intensity less than that. Okay, and you see, okay, the 0 decibel, you can hear that sound if its frequency is 3,500 hertz. If it's 100 hertz, you have to go to 20 decibels before you hear it, and so on. Okay, so this is showing you the frequency dependence. So now we'll talk about interference in sound waves. What is this? What are we talking about here? What is this referring to?
Obstacles in the path or something?
Constructive and destructive interference.
Yeah,
These overlap.
So when does it happen?
When both sides are closed.
When you have multiple sources. Let's say we all talk together, and what does Garrett hear? Okay? So we'll keep it simple. We'll take two speakers and we'll send the same frequency through the speakers. Okay. So, so let's say what this is showing you is one wave is traveling one wave started here, and if you were seated here, this wave traveled that distance. One wave started from here, and if you were seated here, this wave traveled that distance. Okay. So these are two speakers, and you encounter this in all theaters and stuff like that. Okay. So you'll have multiple speakers, and let's say this is your seat. Okay. This wave will travel that distance. This wave will travel this distance. Okay, now if one wave reached you with a crest and the second wave reached you with a trough, that particular frequency will cancel. That's destructive interference. If one wave reached you with a crest and the other wave reached you with a crest as well, those will add up. You'll hear a louder sound. Okay. So when you have multiple speakers at any the energy is getting redistributed. There are some places where, so black dots are purely destructive sounds, purely destructive interference. Purely constructive interference, these are purely constructive interference. So there's zero energy being deposited here and more energy being deposited here. Okay. And those are purely constructive, and purely constructive two troughs. Okay, so these are both purely constructive. All right, so you see whether you have constructive or destructive interference will depend on the path difference. So delta R is the difference in the length of the two paths. Okay, delta R is that. And this is the phase difference. Okay, we won't worry about this formula. This is what's more relevant. Delta R is n lambda. When the path difference is an integer multiple times the wavelength, then you have constructive interference. When the path difference is a half integer times the wavelength, then you have destructive interference. Okay. All right, let me show you this on a ripple tank. Okay. So, all right, so you see this in a ripple tank. You can think of those as two speakers, and along those lines, that frequency, you have destructive interference and you have constructive interference there. Okay, so this is not a academic exercise. This is in an auditorium. If you have two speakers, you don't want to put your seats in along those lines. You want to put your seats there. Okay, so this kind of analysis is done in acoustic designs, in sound engineering. Okay, did you guys understand that? All right, so here's a device where you have a single speaker. You have a part of the wave travel this way, part of the wave travel this way, and you can adjust this, move this arm up and down, and as you move it up and down, you can have constructive and destructive interference. Okay, so you can have sound cancellation and sound enhancement. All right, so here's a question I like to ask. Okay, let's say we have two speakers playing music, and where Alexander is sitting, they completely cancel. How does Alexander know if he's in a destructive interference spot, or is there music playing, or there's nothing sounding? How does he tell the difference?
By moving somewhere else?
Yep, by moving somewhere else. Okay. So if you move somewhere else and it's still silence, if you move everywhere, then no sound is being played. Again, the next phenomenon we'll talk about is the Doppler effect. What is the Doppler effect? What is it?
It's an apparent change in frequency when the source of the sound is moving,
Is that the only way it can happen?
or the observer is moving.
That's right. Any relative motion. Okay? So if you have relative motion, okay, if you're moving towards the source, you will hear a higher frequency than what's produced. If you move away from the source, you will hear a lower frequency than it's produced. And that's the Doppler effect. Okay? All right, so all right, so this is showing you a source. Let's say it's producing 100 hertz frequency. What that means is it would produce 100 crests a second. Okay, so if you stand there and if you're not moving, if this is producing 100 crests a second, 100 crests a second will pass you. What you hear will be the exact same frequency as what's produced. Now let's say if the source starts moving and you're standing here, if this is producing 100 crests a second, more than 100 crests a second will pass you if you're standing there. And if you're standing there, less than 100 crests a second will pass you. So if a source is moving toward you, then you'll hear a higher frequency. If a source is moving away from you, you'll hear less than 100 hertz. Okay? So let's say if a source is producing 100 crests a second, based on your relative motion, less or more than 100 crests a second will pass you. And that's what you hear. That's the frequency you hear. Okay, so that's the Doppler effect. Okay, so when observers and source move toward each other, apparent frequency is higher than the emitted frequency. The Doppler effect is common to all waves and it does not depend on distance. What depends on distance? So the Doppler effect is the pitch difference that you hear. And that doesn't depend on how far away the siren is, for instance. What depends on distance?
Intensity.
Intensity. The loudness depends on intensity. The difference in frequency doesn't depend on distance, okay?
So the pitch doesn't depend on
Right.
distance.
Okay. All right, so here's a formula. What V is the speed of sound in the medium. V0 is the observer's speed. Vs is the source speed. And this formula works, okay, so, okay, now I say speed, but V0 and Vs are positive if you're moving toward each other. So if the source is moving toward the observer, then Vs is positive. If the source is moving away from the observer, Vs is negative. If the observer is moving towards the source, Vo is positive. And if the observer is moving away from the source, Vs is negative. That's the sign convention. Okay? All right, so we'll do one case. Let's say the source and observer are moving toward each other. And then both are positive. This number will be greater than V. This number will be less than V. That fraction will be greater than 1. And the frequency heard will be higher than the emitted frequency. Okay? So that's how the formula works. If neither one of them are moving, they're both 0. That is 1. And the frequency you hear is exactly equal to the frequency emitted. Okay. Okay, so you just have to remember the sign convention and that formula. All right, let's go back to our Doppler effect. Okay, so what is happening here? See, the source is moving there, and as it's moving there, all the crests are sort of jamming up. Let's make the source move faster. Okay, what's happening here? Now the source is moving at the same speed as the wave. And so now you see you have a wall of crests. What's happening here? The source is moving faster than the wave. Now you have a cone of crests. Okay, so remember that, let's say the crests were high pressure regions, okay? So now you have a cone on which you have a pressure spike. Okay, so let me have a sheet of paper. Thank you. All right, so let's say you have a plane flying like that, faster than the speed of sound. The speed of sound is 340 meters per second, about 750 miles an hour. Then what you get is a cone on which the pressure spikes. So this is 1 atmosphere. On the cone surface, you have a higher pressure, and then back here it's lower pressure again. Okay, so that's a shock wave. Yep. So, yeah. So here are various examples. So you can see that. So here's a bullet flying. I guess this is through air. There's a shock wave. I don't know if that's through fluid. Here's a jet plane, and there's a shock wave. Yep. All right, so this diagram illustrates that. So here's the source, and the source has traveled all the way to there, and in the time it took for the source to go from here to there, the wave has only traveled this distance. The source has gone from here to there, the wave has traveled this distance, okay? And you see all the crests are lining up on this cone, and that's the shock wave. So atmospheric pressure, high pressure spike, and then atmospheric pressure, okay? Actually, it pressure spikes and then gets lower and then back to normal, okay? So this is the shock cone, the angle of the shock cone. Sine theta is the speed of sound divided by the speed of the source, okay? So this equation has a solution only when the speed of the source is greater than the speed of sound, okay? So this number has to be less than 1 for this to have a solution. And we define a Mach number. Mach number is the speed of source divided by the speed of sound. Okay? You define Mach numbers generally only when it's greater than 1. Yeah. I mean, in principle, Mach number can be less than 1 as well, but that's not sexy to talk about. Okay. So, smaller this number, smaller the angle. Smaller the shock cone, the faster the object is flying. Okay. So by the way, planes have 2 shock cones, one generated by the nose and one generated by the tail. And so here is the pressure spike, and when the pressure spike passes you, that's when you hear the boom, the sonic boom. So this person hasn't heard a boom yet. This person has heard one boom. This person has heard both the booms. Okay, we'll briefly talk about some musical instruments. Okay, so let me go back to Okay, so now when we talk about musical instruments, here's what we're going to talk about. So here's one wave traveling to the right, and here's another wave traveling to the left. They're two identical waves, meaning they have the same wavelength and frequency. And when you have two waves traveling in the same medium, traveling in opposite direction, what they do is their superposition creates a standing wave. Okay, and this is what happens in all musical instruments. So when you pluck a guitar string, a wave travels to the right, it gets reflected at the fret and travels back to the left. So on the string, you have two waves traveling in the opposite direction. And you get standing waves. So when you pluck a guitar string, here's a guitar string, when you pluck it, here's the lowest mode of frequency it can vibrate, here's the next higher frequency. So these are all standing waves. Okay? Next higher frequency. So if this was 50 hertz, that's 100 hertz, that's 150 hertz, and so on. Now here's the deal. Okay. When you pluck this guitar string, you can never excite only a single mode. You're always exciting a mixture of these. Did you guys understand that? The only time you get a single mode is when you do a tuning fork. So, for instance, if you play the flute or any instrument or the piano, you're never exciting a single mode. Okay, so this is the fundamental. This is the first harmonic, second harmonic, and so on. So, for instance, did you guys understand that? So when you sound a tuning fork, you will excite a single frequency. But when you play any instrument like the flute, so you're exciting a harmonic mixture. When you pluck a guitar string, you're exciting a harmonic mixture. And this mixture is what makes, different instruments sound different. Okay, this is called the timbre of the sound. So if the clarinet sounds tinier than the flute, that's because the higher harmonics have a larger mixture. Yeah. And so that's the difference between, for instance, a $3 million violin versus a $30 violin. This is what you're paying the difference for. Okay, the timbre of the sound. Yeah. All right, so here are the harmonics so for a string, and the frequencies are given by, so the speed of sound on the wave is tension in the string divided mass per unit length. L is the length of the string, and N is an integer. So the frequency you can excite are these guys. So it seems like you can excite only very few frequencies. So how do you play music on the guitar?
You change the length of the string.
That's right, you change the length. That's how you can change the frequency, and then you can also choose which string to play. So that's the thing you have to have control of. Okay, so that's how you produce various frequencies. So here's the instrument where you're exciting an air column. Okay, so this is a flute, for instance. Okay. By the way, these guys are called nodes, and these points are called antinodes. Antinodes are the points which vibrate with greatest amplitude, and nodes do not vibrate at all. So here's a flute, and the air column is excited such that these are antinodes and these are nodes. Okay. So the allowed frequency for a column of air is L is the length of the column, and it's all the harmonics are excited. V is the speed of sound in air divided by 2L. Okay, so those are the frequencies you can excite. Again, these are all standing waves. Okay. So when you play the guitar, you're making the string vibrate, But the vibrating string, the sound it produces, you can't hear that. So for instance, if I played this sound, a guitar here, I've just vibrated the string here, Karina couldn't hear it. So how do I make it her hear it? I gotta have some kind of amplifier. So that's the sound box in an acoustic guitar. Yeah, that's the. In an electric guitar, you use electronics to you convert the vibrations into an electrical signal, and then you amplify them. You know. So all instruments will have something that vibrates that's generating a sound, and they have some kind of amplifier built in. Okay. If you have an air column with one end closed, that's a node, that's an antinode, and the frequencies, only the odd harmonics can be excited. Yeah. So, for air columns and strings, okay, what you have is you excite harmonics. The higher frequencies are integer multiples of the lowest frequency. A drum head is different. So here's the lowest frequency, here's the next higher frequency. See, it's not an integer multiple of the lowest frequency. Here's the next higher frequency and so on. Okay, so these are not harmonics. Okay. Let me show you a so here's a drum head vibrating. Yes. So here's the next higher mode. Okay. And so, okay. So check that app out. It's pretty good. Okay. Again, a drum head, the frequencies do not form a harmonic series. Beats, when two close by frequencies are played simultaneously, so here's two frequencies that are close by that are played simultaneously. When they combine, and what you hear is, see, the intensity level rises and lowers. So what this is showing you is, this is the intensity level is low, here the intensity is high, low, high, and so on. Okay, and the frequency with which the intensity level rises and goes down is the beat frequency, and it's equal to the difference in the two frequencies. Okay, so let's say if you play a tuning fork of frequency 525 hertz and 520 hertz, okay, the intensity level will go up and down 5 times a second. The beat frequency will be 5 hertz. Okay. And you've seen that if you go to a concert, when musicians want to tune the instrument to a particular frequency, they'll sound a tuning fork and they'll adjust the pitch of their instrument to match the frequency of that. Okay, so, and it matches when they don't hear any beats. Okay, so I'll just go over some miscellaneous stuff. Okay, so earthquakes are sound waves, seismic waves are sound waves. So here's an earthquake that happened, it sends out energy. Okay, and you see this wave is traveling to the earth like that. P waves are longitudinal waves, and S waves are transverse waves. First thing, why are they curving? Don't waves travel in straight lines?
Only if the object is of constant density,
Okay, so why is it?
because Earth isn't of constant density.
Okay, so, okay, anytime a wave bends, its velocity changes. That's when it bends. Okay, and for longitudinal waves, you're right. I'm just, yep. And so what Alexander said was right. Okay, so waves bend, this is called refraction, when their velocity changes. Okay, and so for these guys, for P waves, velocity is like that. And see, the velocity depends on bulk modulus and density. So we know the internal structure of the Earth by studying how these waves travel. Okay, you can, from the bending, so an earthquake happened here, and you detected on seismometers all around the world these waves reaching there. You reconstructed the path, and using data from millions of earthquakes, you have all this data, and then you can calculate the velocity as a function of position, and then back calculate the bulk modulus and density. Okay, so that's how come we know the internal structure of the Earth. So this picture, if you were taking a physics class 100 years ago, you wouldn't know this picture. We had no idea about this. Okay. So P waves are longitudinal waves, and their speeds vary from 4 to 7 kilometers. S wave or transverse wave. P standing for primary waves and S for secondary waves, 2 to 5 kilometers. What is this guy? Okay, so it's a transducer. What it does is it converts mechanical energy into electrical energy. Okay, so it converts mechanical waves into electrical impulses there. Okay? And then those impulses are sent to your brain, which are interpreted appropriately. I urge you guys to go see this video. It's pretty good. All right, so this guy is sort of like a lens. It focuses more energy there. So I guess this thing amplifies, I'm not sure, maybe 100-fold. Okay. And so here's energy coming through air. This gets the ear vibrating. And these vibrations have to be transmitted to a fluid in the cochlea. And the most efficient way to do that is through these 3 light bones. Okay, so these bones are touching this eardrum. So as this eardrum vibrates, that is transmitted to the bone, and then that vibration is transmitted to the fluid. Yeah. And on the fluid, so in the cochlea, there's a sort of a long coiled membrane, and as the fluid vibrates, different parts of the membrane vibrate at different frequencies, and that's how all the frequencies are separated. Anyway, an amazing device. You guys should go see the YouTube video. What is echolocation?
Use of sound waves to differentiate what's in the environment.
Yeah. Have you seen or used one? Your motion sensor in the lab is one of them. Okay. So these guys obviously use it. So, okay, here's the deal. You send a sound wave, here's the device, and here's the reflection. Okay, so if you're stationary, and if this is stationary, the reflected wave is the same frequency. If this object is moving toward you, the reflected wave is a higher frequency. Okay, so you send out a sound wave, and if the reflected wave is a higher frequency, this object is coming toward you. The intensity of reflection tells you how far the object is. And the time delay tells you how far away the object is. Okay? So the time delay tells you how far the object is. The intensity tells you how large the object is. And the frequency difference tells you the velocity of the object. Okay? So this guy is emitting ultrasonic waves, and it's looking for three pieces of information in the reflected wave: the frequency shift, the intensity, and the time delay. And from those three pieces of information, it can know how far the object is, how large the object is, and how fast the object is moving. And all that computation is done in this little pea brain. It's not funny. This guy can fly through absolute darkness with all kinds of tree branches and stuff like that. It's, I don't know, 60 miles an hour or something like that. I mean, this is absolutely amazing. Yeah, absolutely amazing. Noise cancellation. This is a wonder of miniature electronics. Okay, so here's a sound coming from outside that you don't want to hear. You only want to hear the music that's fed through your appliance. So you want to cancel this sound, and here's how noise cancellation works. You first sample the sound you want to cancel, and then using your electronics, you generate an opposite wave. And so that's the external sound, and you generate this green wave, and out of phase, and they're canceling each other. Okay. So noise cancellation, it works best for low frequencies. And it's hard to cancel this high-pitched screeches and stuff like that. So you could have a noise cancellation headgear, and if some car drives by and screeches comes to a screeching halt, you'll hear that. Okay, so sound localization, this is you, let's say you have your eyes closed. If something makes a sound here, you can tell that's where the sound is made. And the information used is this sound reached to your left ear first, and this sound reached later. This sound, when it went through your head, its intensity was lower. And if this wave reached from here, which reached you a lot later. So all that information is used by your brain to localize the sound. Okay. It turns out that you guys have subwoofers in your homes and stuff like that. Okay, so the speed of sound is frequency times wavelength. And by the way, you can locate a source only within a distance roughly the wavelength. Okay, so if the frequency is 100 hertz and this is 340 hertz, the wavelength is 3.5 meters. 3.5 meters is the length of these two tables. 3.5 meters, 4 meters. 4 meters is actually roughly the length of these two tables. So a speaker that's playing 100 hertz, you can't tell where it is within 4 meters. Did you guys understand that? So that's why you can put the subwoofer anywhere you want. Okay. All right. So the timbre of sound, what this is showing you is a tuning fork, the flute, and the clarinet playing the same note. How do you tell the difference? From the harmonic mixture. Okay. The timbre is the harmonic mixture of the sound. I'll let you guys read that stuff. Okay. Here's a classification of singers. So sopranos sing at that frequencies, alto at that frequencies, tenors at that frequency, and so on. That's the range. Okay. All right, guys. Sorry to load you guys up, but that's how it was.